Okay, let's dive into this. Welcome to today's Explainer, where we're tackling one of the most massive, yet completely invisible challenges of our modern world: modernizing the electrical grid. I mean, we rely on electricity for absolutely everything, right? But the gap between the power we can actually generate and the power we demand is widening rapidly. And this gap is pushing our aging infrastructure right to the brink. So today, we're going to look at how engineers are borrowing a page directly from biology, specifically Charles Darwin's theory of evolution, to mathematically design a smarter, much more resilient power grid. Here is our roadmap for the Explainer. We'll quickly start with the power grid dilemma, then look at the local generation fix, uncover some hidden grid dangers, bring in genetic algorithms to the rescue, and finally find that perfect power placement.
Section 1. The Power Grid Dilemma.
Now, when the gap between power generation and customer load gets too wide, we risk severe system strain and some pretty dangerous blackouts. To really ground us in the incredible scale of this infrastructure, just think about this number: 237.742 gigawatts. That was India's massive installed electricity capacity as of early 2014, making it the fourth largest in the entire world. Yet despite having that colossal number, grids still struggle. And it's really because of how that power is generated and moved around.
Historically, a massive 87.55% of that capacity comes from non-renewable, highly centralized power plants. This huge reliance on just a few giant plants means power has to be shipped over incredibly long distances through transmission and distribution lines. When peak demand suddenly surges, while those long-distance lines experience major bottlenecks, severe voltage drops, and honestly, massive energy losses just from the pure physical friction of moving electrons miles and miles down a wire.
Section 2. The Local Generation Fix.
So, if incredibly long power lines from giant centralized plants are the problem, the seemingly obvious fix is just generating power right where it's actually being used, right? And this brings us to a concept called distributed generation, or DG. Instead of relying entirely on a distant coal or gas plant, distributed generation places small-scale power generators, anything from 1 kilowatt up to 50 megawatts, directly within the local distribution system, right next to the customers. We're talking about integrating local solar panels, wind turbines, fuel cells, or even microturbines directly into our neighborhoods and industrial parks.
And this brilliantly illustrates why adding local power sources sounds like the perfect engineering fix. By placing generation right near the load, utilities get this incredible flexibility. It seriously improves localized reliability, takes a heavy strain off existing substation transformers, and dramatically lowers those transmission line losses we just talked about. Because the power literally doesn't have to travel far, the overall voltage profile and power quality experienced by the customer are beautifully enhanced.
But it's not quite that simple. Section 3. The hidden grid dangers.
It turns out you absolutely cannot just plug these local generators into the grid wherever you feel like it. See, our power networks were historically designed to be radial, which basically means power is only supposed to flow in one direction, from the big central station straight down to the consumer. Think of the distribution grid like a network of one-way streets. When you improperly place a distributed generator, you're suddenly pumping a massive traffic jam of local electrons onto a small grid road that just wasn't built for it. If the local generator produces more power than the neighborhood is using right at that moment, the excess power literally forces its way backwards up the grid. This causes a huge traffic jam called reverse power flow. And just like water pressure building up in a blocked pipe, this reverse flow causes highly dangerous voltage spikes, or voltage rise, which can fry equipment and actually trigger protective relays to shut the whole system down.
Let me just show you exactly how bad a bad guess can actually be. 82.82 kilowatts of total power loss. In a standard test of a 15-bus grid network, if you just kind of guess and improperly place a 1.2 megawatt generator at a random location called bus 13, the power losses across the grid actually skyrocket to nearly 83 kilowatts. To put that into perspective, if you did absolutely nothing, zero local generation added at all, the baseline losses were only 62.12 kilowatts. So by guessing the wrong location, we actually made the grid significantly worse.
Section 4. Genetic algorithms to the rescue.
The grid is simply way too complex to guess where to put these generators. The math is completely nonlinear, so changing one tiny variable throws off everything else. So engineers turned to something amazing: a genetic algorithm, or GA. This is a computational search technique that's actually based on the mechanics of natural selection. Instead of trying to brute force a math equation, we're going to let the math evolve. We are literally going to use the biological rule of survival of the fittest to organically evolve the absolute best possible layout for our power grid.
Here's exactly how we apply biology to mathematics. The algorithm starts by generating a totally random population of chromosomes. In our case, a chromosome is just a random guess of where to put a generator and how big it should be. First up is evaluation. The system runs a power flow test to see how fit or good that guess is at reducing power losses. Second is selection. The algorithm ruthlessly kills off the bad guesses and keeps the fittest ones. Third is crossover. It takes the absolute best traits from the surviving guesses and breeds them together to create offspring solutions. And finally, mutation. It makes tiny, random tweaks to ensure we explore every single possibility. It runs this evolution cycle over and over, testing thousands of generations until it breeds the ultimate, mathematically perfect solution.
Section 5. The perfect power placement.
So what actually happens when we unleash this evolutionary math onto a standard 15-bus system? Well, before we look at the results, let's briefly demystify some of the technical jargon we're dealing with. The algorithm had to choose what type of power to inject. The ideal candidate the system identified is called a P plus JQ generator. Simply put, this is a generator, kind of like a synchronous machine, that supplies both real, working power, the stuff that turns your blender on, and reactive power, which is a stabilizing force that maintains the grid's overall voltage pressure.
Now, what's really interesting about this slide is how distinctly the different generator types perform. The algorithm tested generators supplying just active power, which left our grid losses around 36 kilowatts. It tested generators consuming reactive power, which actually made things worse, resulting in almost 55 kilowatts of loss. But that P plus JQ generator? It drastically outperforms the others, pushing total system power losses all the way down to a staggering 17.08 kilowatts.
Let's celebrate this incredible drop for a second. 17.08 kilowatts. Remember, our baseline loss doing absolutely nothing was over 62 kilowatts. By simulating generations of evolution, the genetic algorithm found the exact optimal sweet spot, bus 3, and it determined the exact optimal size, a 1.0 megawatt generator. By dropping this specific generator into this highly specific mathematical sweet spot, line losses dropped dramatically, and the voltage profile across the entire network smoothed out perfectly.
So the crucial point is the stark contrast we end up with here. Doing nothing leaves us bleeding 62.12 kilowatts of wasted energy. Guessing wrong and improperly placing a generator spikes our losses to a very dangerous 82.82 kilowatts. But by using evolutionary mathematics to upgrade our infrastructure, we completely optimize the grid. We place a 1 megawatt generator at bus 3, and we slash our losses to just 17.08 kilowatts. It's a massive leap in efficiency. It saves energy, it heavily reduces costs, and it absolutely prevents grid failure.
We've seen today how the principles of biological evolution can literally keep our lights on. By mimicking the survival of the fittest, we can solve the incredible mathematical complexities of the electrical grid. But it really leaves us with a fascinating question. If genetic algorithms can perfectly optimize where we generate our power, what other invisible infrastructures in our cities, from our complex water pipelines to our chaotic traffic grids, are just sitting there waiting for their own genetic evolution? Thank you so much for exploring this with me today, and keep questioning the engineering miracles around you.